All right, so let's go ahead and get started again. So before break, we were looking at this Hess's law problem, and we said that the first equation given was perfect, but the second one needed to be flipped. And when we flipped it, we changed the sign of the delta H value. And then after we did that, we crossed out anything we saw on the right and again on the left, and then we added up the values of delta H. So any questions about what we've done so far with this problem or with Hess's law in general? All right, so remember Hess's law, it takes a while, so just make sure you get some practice on it. And of course, I'm going to give you some practice on it with the homework. All right, so here is another Hess's law problem. So it says determine the enthalpy of the reaction for this equation right here. All right, so that is our overall reaction. That is the reaction we want to build. And here we have 1, 2, 3 chemical reactions. And let me actually give myself a little space here. So those are the 3 reactions that we're going to use to build our overall reaction. All right. So we talked about before how there's a lot of different ways to do Hess's law. The way I like to do it is just march through the overall reaction, start on the left, march all the way to the right. So let's give that a shot. And I'm going to start with this carbon right here. So where do we see free carbon? Carbon that's not attached to anything else in reaction 1, 2, or 3? All right, so I'm seeing some 2s. Excellent. So I see it right over here. So first of all, do we have any other free carbons in any of the other reactions that we need to worry about? Is there any in number 1 or 3 where it's just a carbon by itself? And I see lots of no's coming in. That's excellent. So it's only reaction 2. And by the way, if you ever see it in some other reactions as well, I'm going to tell you to leave that one until the end. All right. So here we're dealing with our carbon. We know it is in reaction number 2. Is it on the correct side? Are they both reactants or both products? Excellent. So I'm seeing yeses come in. Perfect. So here we have a reactant that's carbon, and here we have a reactant that's carbon. So it is on the correct side. Do we have the correct number? All right, so I see a no from Tasso, and Tasso is correct. So and I see Juan saying times 2. That is exactly what we're going to do. We needed 2 carbons, but we only had 1. So what we're going to do is multiply this entire reaction by 2, and we will also multiply the delta H by 2. So now I'm going to rewrite number 2 down here. Let me actually change it back to blue. And I am going to multiply everything by 2. So I'm going to say there's 2 carbons plus 2 oxygens, 2 O2s I should say, going on to 2 CO2s. So I have doubled everything, and now we're going to double the delta H. So we're going to say 2 times delta H2, and then we're going to actually do that calculation. So it looks like negative 394 times 2, and now we have negative, looks like 788 kilojoules like so. All right, so any questions about what I did to equation number 2 or why I did it? All right, so next up, as I said, we're just marching left to right through our equation. I'm going to move on to our H2 over here. All right, so where is H2? Which equation, 1, 2, or 3? Excellent. So I'm seeing some 3s coming through. So here it is right here. So it is in number 3. Are there any other H2s we have to worry about? Is there any other H2s showing up in equation 1 or 2? Excellent. So this is our only H2 that we have to deal with. Now, is the H2 on the correct side? Here. All right, so I'm seeing a yes from Tasso, and that is correct, and a yes from Angie and Kimberly as well. So H2 is a reactant, and H2 is still a reactant. So that's good news. Now the problem here is how many. So in our overall reaction, it says we're supposed to have 3, but we actually have 2. So I want to take a moment, just a brief moment, to talk about the math there. So right now we have 2 and we need to have 3. So if I multiply this by 3/2, we can cancel out our 2's and we will end up with 3. So what we're going to end up multiplying in is this right here. We will multiply in 3/2. Any questions on why we're going to use 3/2 as the number we're multiplying through? All right, so I know that's a weird one, but let's go ahead and give this a try. So we are going to multiply 3/2 into this. And I'll go ahead and use green. So 3/2 times our equation, and then 3/2 times our delta H. And if you're wondering, yes, you can use 1.5 instead of 3/2. So now let's rewrite number 3. So 3/2 times 2 hydrogen will give us 3 of those hydrogen, or H2. For the oxygen, rather than say 3/2, I think it's easier to talk about it as 1.5. So I'm going to go ahead and call that 1.5. And then on the other hand, 2 times 3/2 will again give us 3. In this case, of our H2Os. Let me write that arrow. Then we're going to do 3/2 times our H3. So I'm going to do 3/2 times negative 572. And it looks like we have negative 585. No, I'm sorry, 858. I apologize. All right, negative 858. Any questions on how I did that math in my calculator to do 3/2 times the 572? All right. All right, so any questions about what we've done so far? I'm going to go ahead and move these over a little bit. There we go. All right. So next up, we're going to do our C2H6. And we've already done number 2 and 3, so I'm hoping that we find C2H6 in our first equation. And we do right over here. So then that's the only place we see C2H6. So first question is it on the correct side? All right, so I see several no's coming in. Excellent. It is on the wrong side, which means we are going to need to flip this over. Do we have the correct number? Excellent. So I see some no's coming in. So we are supposed to have 1. When there's no number in front, that means a 1, but we actually have a 2. So what we're going to do is multiply the entire thing by 1/2, or if you prefer, 0.5. And let me get a different color so we can color code a little bit. So the entire thing is going to get multiplied by 1/2, including its delta H value. All right. Oops, and I forgot the delta H value also needs a negative out here because we are going to flip its sign. All right. So now let's write number 1. So half of 2 will give us, oh, I'm sorry. Let me go ahead and start with this right over here. So we have 4 CO2, and I'm going to turn that into 2 CO2, so I'm cutting those in half. We have 6 waters, and I'm going to turn that into 3 waters. And on the product side, we had 2 of the C2H6, and we're going to turn that into 1 C2H6, and 7 O2 divided by 2. So that will be 7/2 or 3.5 O2 like so. All right, any question to what I did with the equation, first of all? All right, so next up we're going to take a negative 1/2 times our delta H1. So let's go ahead and do that together. So I'm going to do negative 0.5, and I'll be multiplying that by our negative, and it looks like 3120, and it looks like we're going to get a positive 1560 here. All right, questions on anything that I've done so far? All right, let me get this math out of our way. So if we've done this correctly, and what we're about to do is our double check to make sure we did it correctly, we should be able to cancel out everything that appears on both the right and the left side, everything that's identical from the left to the right, and then we will end up with our original reaction that we wanted to have, which is the overall reaction. So is there anything that we can cross out? What do y'all think? Is there anything you see in here that we could cross out? All right, so I see H2O and CO2. So here is 3H2O and 3H2O. And let's move on to that CO2. So I see 2 CO2s and 2 CO2s. Anything else that we might be able to cross out? All right, and I hear O2 from Juan and Kimberly. Excellent. So let's talk about that. Trying to find a new color we haven't used, orange. Okay. So if we combine 2 plus 1.5, do y'all agree that would be 3.5? 2 plus 1.5? Excellent. And over here we have 3.5 O2 as well. Sometimes you have to combine the elements on one side to equal that of the other. So let's just say, for example, you didn't catch that and you brought it all down. And so here's 2 carbon plus 3H2 plus 2 plus 1.5 gives us 3.5 O2. Going on to C2H6 plus 3.5 O2. So now when we look at it, we can see that 3.5 on both sides. All right, so I'm going to bring it down one more time and say there's 2 carbons plus 3 of our H2 going on to C2H6. And before I do any of that math, I'm going to go ahead and check and make sure that we did this correctly. The way we do that is we look up at the top, and we have 2 carbons, 3 hydrogens, or I should say 3 H2s, and then C2H6. This is correct. So we are ready to add up our numbers. But any questions on anything that we've done so far? All right, so now for the math part, and I'm just going to bring it down so we have a little more space for it. So here it is, 1560 minus or plus a negative 788 plus a negative 858. Go ahead and add up the kilojoules for our overall reaction, and I'm going to move this math further out of our way. There we go. So you are looking at this right now. So go ahead and add that up, and I'm seeing some negative 86 kilojoules come through. So what do you all think? Is everybody getting something similar to negative 86? I see Tasso and Juan got that. How about anybody else? Do you want to confirm or deny that negative 86? All right, so it looks like Maria says yes, Tasso says don't trust me, and Angie says yes. All right. How about the rest of you? Is everybody able to find that negative 86 kilojoules? Excellent. How do our sig figs look? What do y'all think of those sig figs? All right, so Maria says good, excellent. So here we're doing addition, subtraction. So thank you, Tassa, looks good as well. Okay, so addition, subtraction, so that means we're counting digits after the decimal. No digits after the decimal for our delta H value, so no digits after the decimal for our overall delta H. And again, this is going to be our delta H overall. All right, so questions on anything here? All right, so I know, again, Hess's Law tends not to be a crowd favorite, but how are y'all feeling about Hess's Law so far? Seem like it could possibly be doable by the time you get to your exam 2 weeks from today? All right, so Tassa sounds like he's doing okay, and the rest of you are too scared to type in. All right. So again, if you're thinking, hey, this is really tough, I need some more help on that. Let's see. So YouTube can be very helpful as well. Yes. So 8, let's see, 8, 10.
I have a question.
Oh, yes.
For when we multiply equation 1 with the 1/2.
Yes.
Why was it negative 1/2?
So the negative came from the flip. So anytime you flip.
Flip it. Okay.
Yes, exactly.
And we flip the sign. Okay, sounds good. Thank you.
Mm-hmm. And Kayla, was this the slide that you wanted to see? Okay. Just let me know when you're done. So Hess's Law definitely needs a little bit of practice, but once you master it, you will have mastered it, and then you won't be struggling as you move on to 1B, because again, you're going to see this again in 1B. All right. So questions on anything so far? All right, so next up, types of enthalpy. So I promised you that we would come back to that delta H of formation, and here it is. So for the heat of formation, so delta H of formation is also called the heat of formation. The energy released or absorbed when a compound is formed from elements in their standard state. So let me show you what I mean. So let's say I was talking about making some NaCl, some table salt. What it is going to start with are the elements in their standard state. So sodium in its standard state is a solid, and chlorine its standard state is Cl2 gas. And I'm going to go ahead and put a 1/2 in front of here just to balance it out. And the reason is I want to produce this. And so in its standard state, sodium is a solid, chlorine is Cl2, but that 1/2 is to balance because I only want 1 mole of NaCl. So anytime that we're looking at delta H of formation, and you will see this little knot here, and I like to think of that knot as actually a O for original. So it is how these elements were originally, how we would find them in nature. So we're going to keep working on this for a while, but any questions so far? Yes, these are the standard states, and they do still come from the periodic table, yes. So other questions so far? All right, so you saw this slide once upon a time. I believe it was chapter 1 or 2, but it is back. So I need you to know what the standard states of each element are. So here are gases. So gases, hydrogen, nitrogen, oxygen, fluorine, chlorine, and all of our noble gases. Also need you to know our liquids. We only have 2 of them, mercury and bromine. Solids are everything else from the periodic table. So again, these are the same standard states you learned way back in chapters 1 or 2. So questions on anything so far? All right, so we will be able to use this delta H of formation to find the enthalpy of a reaction. So we have been finding this value right here using Hess's law, but there is another way. I know this is a much more popular way. It's an easier way, but what I'm going to warn you is on a test, you're only going to be given enough information to either use Hess's law or to use this method. So you, as a student, unfortunately, you don't usually have the choice of which one you want to do. You've got to use the one that we give you. That's a sad thing about being a student. You don't have as many choices. Okay. So here we're using the idea that it is a state function. And what we're going to do is only deal with products and reactants. So we're going to take the products, we're going to subtract out the reactants. So this equation here looks long and scary, especially with those summation signs in it. What I'm going to tell you is you don't need to memorize that equation. All it is saying is add up the delta H values for all your products, add up the delta H for all your reactants, and subtract the two. And the reason that n is in there is because if there's a coefficient, you need to multiply it in. So again, it is not as bad as this equation makes it sound. All right, so this is the table that we're going to use. You have a similar one in your textbook. If you don't have the textbook, feel free to Google a enthalpy of formation table. Just literally type in enthalpy of formation table. You're going to get lots of them coming up. But there is something very important that's underneath here. And that is an element in the standard state has an enthalpy of formation of 0. So what we're saying is, let's say we're looking for the enthalpy of formation for hydrogen. Well, it's formed from the hydrogen that we have on Earth, which is H2. And because it's H2 to H2, delta H of formation would be 0. Likewise, if I wanted the enthalpy of formation for sodium as a solid, well, the standard state is already sodium as a solid. So again, delta H of formation would be a 0. So one sort of, I don't want to say shortcut, but way to remember this is if it's not on the table, it's probably a 0. So if it's something that you need for your equation and it is not on that table, very likely it is a 0. It's something in its standard state. Okay, so we're going to come back to this table as we solve our problems, but any questions on anything so far? All right. So here's our first reaction. It says find the enthalpy of reaction for the following reaction. All right. So what we want to do is add up all the delta H values for the reactants and add them all up for the products, and then we will do products minus reactants. All right, so the first thing I'm going to do is write it out more formally, just so you have it in your notes. You don't have to write this out for me. So I'm going to say delta H of formation for the CO2 minus delta H of formation for the carbon as graphite plus delta H of formation for the O2, and these are our products minus reactants. So again, the way I recommend that you remember these is simply as products minus reactants. All right, so questions on anything so far that we've done? All right, so next up, products, CO2. So we're going to look up CO2 on the table. Here's our carbon dioxide, and it is negative 393.5. And this is in kilojoules. By the way, your unit will always be on the top of your table. So here are those units right here, kilojoules or kilojoules per mole. Either one is fine with me. Minus, and I realize that most of you aren't familiar enough with carbon to know, but carbon as graphite is in its standard state, so that will be 0. And by the way, that's not something I expect you to memorize. I would put a note on the test that would say carbonous graphite is in its standard state, or I would literally say it was 0, because I don't expect you to remember all the elements that have funky standard states. All right, but I would expect you to know that O2 is the standard state of oxygen, so that is also 0. So here, negative 393 minus 0, negative 393.5 is going to be our answer, and that is delta H for our overall reaction. All right, so any questions? It's not 0 in its standard state. So Jervin, CO2. So Jervin has a great question about CO2. So CO2 is not in its standard state because that's both carbon and oxygen. What would happen is it would need to have carbon plus oxygen, like so. So any molecule is not in its standard state. The only things that can be in their standard state would be an element. So carbon by itself or oxygen by itself. All right, so other questions on anything so far? All right, so as you can see, this takes a lot less time, and probably less time and energy than Hess's law, but I do want you to know how to do both of them. All right, so let's try one that's got some coefficients in here. So again, I'm going to write it out formally first. You don't have to write all of this out for me. All right, so I'm going to do products minus reactants. So I'm going to start with the CO2, and I'm going to say 3 times delta H of formation for CO2 plus 4 times delta H of formation for H2O as a liquid. Notice I did list water's state, and water is the one that I want you to always double check its state. And the reason is, if you're looking at any given table, there's a very good chance water is going to be listed 3 times. So it's going to be listed as a solid, a liquid, and a gas. So always double check that you're getting the correct one, that you're getting whichever state it is that you need. All right, so all of these are our products. And we will subtract out our reactants. All right, so here we're going to have 3 times the delta H of formation for C3H8 plus 5 times the delta H of formation for O2, like so, and these are our reactants. All right, so questions on anything here so far? Okay, so I'm going to try to do a split screen so we can get both this and the table in at the same time. Give me just a sec here. All right, so not perfect, but I'm going to expand and contract as we go. So the first thing that we need is CO2. And there it was, already highlighted, negative 393.5. Now in our problem, we have 3 times that value of CO2. So I'm going to say 3 times negative 393.5. And what I'm going to do, because everything has the same unit, is I'm going to leave the units till the end, and I'll tack them on at the end. But any questions about that CO2, about why I multiplied it by 3 or anything else? All right, so next time we're going to, or I should, next thing that we have here is 4 times our value for water as a liquid. So it's going to be 4 times. And notice here we have water and water vapor, but we said we need water as a liquid. So we're going to take negative 285.8, but I want to point out the other one, and the reason is if we were in class, I would probably have you doing this at your table, and probably at least 20% of you would grab the wrong value. You'd grab the gas instead of the liquid. So be really careful with that water. Always make sure you grab the correct state. So for us, we want this one right here, negative 285.8. All right. So any questions about what we've done so far, finding our value for CO2, multiplying it by 3, and our value for water as a liquid and multiplying it by 4? All right. So now we're going to subtract out our reactants. And the first reactant, we're going to multiply 3 times, and it looks like it's C3H8. And here it is, listed under propane. There we go. All right. And you may remember propane from way back when we did organic nomenclature. So prop means 3, ane means all single bonds. So C3H8, it looks like it is negative 103.85. By the way, I hope I'm not making anybody dizzy by the zooming in, zooming out. If it's bugging you, please do let me know. All right, so plus 5 times, what is the delta H formation value for oxygen? 0, excellent. All right, so I have written this out just in lots of detail. So you can see everything I did. Those of you who immediately realize that oxygen is 0, you can just go ahead and cross it out. But I just, again, did all of this so that we could take a look at how it's all laid out. So what I'd like you to do next is to calculate this out. So 3 times negative 393.5 plus 4 times negative 285.8, all of that together, and then you're subtracting 3 times negative 103.85, and I'll tack on the units all the way at the end. It is in kilojoules, or you can say kilojoules per mole. So go ahead and find our delta H of reaction in kilojoules. So I hear a question on why there's a 3 in, oh my goodness, because I was looking at CO2, thank you. All right, so if you guys are calculating, I made a mistake here, thank you, Clinton. Somehow I took this 3 and I did something strange with it. There was no coefficient in front of the propane, and it should indeed be a 1, thank you. So for those of you calculating, be careful, I accidentally put a 3 here that shouldn't have been. So please take out that 3, and I apologize if you're calculating, go ahead and recalculate with a 1 there. Thank you, Clinton. You guys got to keep me honest when I do crazy things. By the way, I always appreciate when you guys catch my mistakes, and I apologize about that. It's really hot in here. I didn't want to open the window because it's kind of noisy outside. Hopefully you can't hear my neighbor's music through the wall. All right, anyone get an answer now that we have that corrected and we got rid of that 3? All right, so I'm seeing a 2,226. Anyone else get a similar or different answer? Anyone else want to confirm or deny that answer, or should I calculate that out for us? All right, so let's go ahead and calculate that together then. All right, so it looks like we've got 3 times negative 393.5 plus 4 times negative 285.8. So that's the first part. And then minus a negative becomes a positive. And then 103.85. And looks like I'm getting negative 2,219 or 2,220. So I'm getting something similar. How about the rest of you? What are you getting? All right. So, all right. And yep. So it looks like everybody's getting something in that range. So, Jervin, feel free to recalculate that. But it looks like, let's go ahead and go with 1 digit after the decimal. So 2,200, and I'm going to say 20.0 like so. Or actually, let's see. Nope. I apologize for my poor rounding there. 2,219.9 would be better. All right. So, then I forgot my negative there. Negative. There's my negative. All right. Any questions on this, or anybody still getting different values? Okay. Well, let me go ahead and write that out a little neater. All right, so any questions on how we're doing the delta H of reaction using our delta H of formation? All right, so to do a problem like this, you would get your values here. The only values that I would want you to know are the ones that are 0. So anytime you have an element in its standard state, it will be 0. So again, if you need a value that's not in your table, it is probably a 0 because it's probably in its standard state. All right, so questions on anything here? All right, so let's go ahead and take a break. So it is almost 7:45, so let's come back at 7:55. And I'm going to step outside just to get a little air because it's so hot in here. So I will be right back. Okay, yeah. So let's see, Jervin, did you put in something similar to what I have in the calculator here? Oh, you want to see the problem again? All right, yeah, give it a try. Type that in one more time.